Hello dear Stata users, in this tutorial I would like to show you how to correctly specify your XTPMG command with different optimal number of flags for your dependent and independent variables. So as you know, XTPMG is used for panel ARDL with pooled mean group option, and this estimation assumes that long-run coefficients are homogeneous across cross-sectional units, and short-run coefficients are heterogeneous across cross-sectional units. So let me first quickly download my data into Stata and introduce my data. So I have 5 countries and 4 variables: real GDP per capita growth rate, which is my dependent variable, savings, gross domestic savings as a percentage of GDP is my first independent variable, value of credit as percentage of GDP is my second independent variable, and trade openness, which is value of import and export as a percentage of GDP. So I download my data into Stata. I just copy and paste it into Stata. Data editor, and paste. So you see my country ID is from 1 to 5. So I have 5 countries, and each country has 24 years of observations from 1996 to 2019. So these are my data sets. Yeah, I think it's strongly balanced. So first I have to declare Stata that I have downloaded balanced data. Sorry, XTset country ID and the year. So you specify cross-country section and time series section. So Stata recognizes it as strongly balanced data. If we look at XTPMG command, you can see examples of how it should be typed. So for example, in XTPMG followed by first difference of your independent variable, first difference of your independent variable, first difference of your last independent variable. So the first part is responsible for short-run coefficients, and the second part is for long-run coefficients. LR stands for long run, and followed by first lag of your dependent variable, your independent variable without any lags and differences, and your third independent variable, sorry. And here we specify our option, which is PMG, and we also need to specify error correction, which is long run, and speed of adjustment from short run deviations to long run cointegration. So here we just specify our data. Here we have as our dependent variable real GDP per capita growth rate. savings, credit, and we have fourth variable, which is trade. We do the same in this part. Savings, credit, trade. Insert, replace. So these are our coefficients. Savings has a negative relationship with change in real GDP per capita growth rate, but statistically insignificant. Credit has negative relationship, but statistically significant, and the trade has a positive relationship, and it is also statistically significant. This is our long run part, error correction coefficient. This is our short run part. This is a error correction term, which is speed of adjustment of short run shocks into long run cointegration. But this is very simple because it is already specified as default command for XTPMG, and first difference here means first lag. But what if we have different optimal number of lags for our dependent and the independent variables, which is different from 1? What if we have, for example, 2 optimal number of lags for our dependent variable and a 3 optimal number of lags for our independent variable? Look, for example, what we just have done is this optimal number of lags for our ARDL. Red one is for our dependent variable, and the green ones are our independent variable. But how our command will look like if our optimal number of lags is like this. For example, if you use eViews, you don't have to worry about it because in Stata, XTPMG is a user-written command. You have to type it manually, but in eViews, it is automatically performed. That's why you don't have to worry about it. So, how to do this in Stata? In order to correctly do this in Stata, we first have to generate new variables, lagged variables of our dependent and the independent variables. So generate, let's call it lag1 of our real GDP per capita growth. Yeah, real GDP per capita growth, which is equal to L dot is our command, real GDP per capita growth rate. If we browse our data, you see that we have lag1 for our real GDP per capita growth rate. And we have to generate lag1 for our independent variables as well. L dot savings. But since we want to specify 3 lags for our first independent variables, we also have to generate second lag of our first independent variables. Here we just call it lag2 of savings, and here we specify L2. If you look at our data, you see that here we have lag 1 for savings and lag 2 for savings as well. Now we go to our second our second independent variable is credit, and here we also have to specify credit, lag 2 for credit as well, lag 2, lag 2. You see, because we have 3 lags for credit and 3 lags for our third independent variable, which is trade. Trade. Lag 1 for trade and lag 2 for trade. Now we run our XTPMG command again, but do the following changes. This will be left as it is, but we have to add new variables. So this is already lag 1 for our real GDP per capita growth rate. So we have to add lag 2 for our real GDP per capita growth rate. How we do it? D dot real GDP, but lag 1. So this is lag 1, this is lag 2, because first difference minus lag 1. So first difference of lag 1. Then this is our first lag for savings. We have to do 3 lags for savings. That's why we do the same for our savings. D dot for savings. And we have the same for credit. Credit. D dot trade and then D dot for lag 2 trade. So this is lag 1 for trade, lag 2 for trade, lag 3 for trade. I will also show this performed automatically in eViews, and we will have the same results in Stata and in eViews. And I just paste long run part as it is. We don't do any changes in long run part. Choosing optimal number of lags is important in pooled mean group estimation, because if you look at long run coefficient for savings, you see that it becomes positive and statistically significant. If you remember, when we performed this command with 1 lag only, savings had negative and statistically insignificant coefficient. This is for 1111 ARDL. So the results for this ARDL and this ARDL is differ from each other. That's why it is very important. So why this is 1111? Let's just do exactly this estimation in eViews. So this is my eViews. I want to download my data. So my start year is 1996, my end year is 2019, and I have balanced panel data, which consists of 5 cross-section units. Okay, and I paste my data from Excel. Here I only have to copy my variables from first country to fifth one. Yeah, here I just paste it from here. Now I highlight my variables. This is I highlight this one first because it's my dependent variable. Savings my independent, credit is independent, and the trade is independent variable as well. I open it as equation. Here I choose method which is PMG, Pooled Mean Group ARDL, and let's say I will do just one leg for dependent and one leg for independent variables or regressors. Okay, so here we have, as I told you, ARDL 1111, and you see we in short run part we have first difference of savings, first difference of credit, and first difference of trade. That's why this part is also 1111. Let's just compare results from Stata and the eViews for ARDL 1111. You can see that they are exactly the same. So here we have 0.06 in long run part for savings and the probability insignificant. This is exactly the same in Stata. For credit, we also have negative result in eViews, 0.20, and statistically significant result. This is identical in Stata as well. Let's just look at first difference of credit in short run is positively related with our real GDP per capita growth rate. So first difference of credit in Stata generates the same result and it is statistically significant. So first difference of credit is positively related with difference in real GDP per capita growth rate or change in real GDP per capita growth rate. Now let's change a little bit our estimation in eViews because it is performed automatically. We can just, for example, for dependent variable, we can do maximum number of lags of 2, and for regressors, we do maximum number of 3. So you see ARDL 2333. ARDL 2333, 2 for dependent and 333 for 3 independent variables, which we have done in Stata. You see, this is first difference, this is second difference for our dependent variable, this is first, second, and third independent optimal number of lags, sorry, for our first independent variable, and so on. Now just compare our results which we have done which we typed manually in Stata with eViews which have done it automatically. So here we see that for savings 0.11 and statistically significant. Here we also see 0.11 and statistically significant. What about credit? It is also identical, 0.17 with minus sign and statistically significant. 0 point minus statistically significant. So here, look, first difference of real GDP per capita grows with lag 1. So this is already lag 2 for our dependent variable. For savings, you see lag 1, lag 2, because it's already first difference, which is lag 1 and the minus 1. Lag behind. And the lag 3 for savings, because first difference and the minus 2. Let's look at this one as well. So lag 1, lag 2 for real GDP per capita is minus 0.0005. This is the same here, 0.0005. And this part, which is speed of adjustment to long Ranka integration, is also identical in both cases. In savings, for example, first lag, second lag, third lag. Let's look at the first lag, which is 0.55, 0.55. Second lag 0.08, 0.08. Third lag 0.08, 0.08, and so on. So just if you want to choose different optimal number of lags, you can use this command. Thank you for watching this video. Do like and subscribe to my channel. It will be very, very appreciated. Bye.